Okay, I welcome you all, and I would like to continue our discussion on time-dependent perturbation theory. And in our previous class, what we have done, we have obtained an expression for the amplitude of the perturbed system. Now, before I go on with this crazy mathematics, let me give you another glimpse of. I want to talk about a person who belongs to this country, a person whose name was. I would reveal his name in a couple of minutes. And this man, it's believed, maybe it has come from the stories, that this man had an imaginative thought experiment. And this thought experiment was, it was based on a candle that has a flame. In fact, there is another inspirational story I can tell you about this candle carrying a flame. But before that, let me focus on this one. And probably this was the time of wars. It was in 1940s time. The war in the world was it was on its peak, and people were involved in playing wars, killing each other, playing politics and all that. But this man was sitting in his room, and he was trying to understand something. And he was sitting in a room in Princeton. And this man had an origin from India. And his name was Subramaniam Chandrasekhar. He was a thin, flat man, but a very good thinker. And in fact, maybe this thought experiment has given him an idea. The thought experiment of a candle, having a flame. Now, if I have a candle, it has a flame, even a small whisper is capable of disturbing this flame. Not only disturbing the flame, it can shut the flame of your candle. And what this man believed that a small disturbance, because he was trying to understand the instabilities of the stars. The world was running with wars, but this man was thinking about the instability. And he was able to guess a very, very strong argument about instabilities. And what was the argument? The argument was that if a small whisper is capable of creating a big change in the candle, the flame of the candle, the small perturbation can decide whether a star will shine its light for millions of years, or this star will turn into a black hole. A small disturbance in the star, a small perturbation. See, we are discussing the quantum mechanical perturbation, but this man was again looking for that perturbation, that a small change in a star can make this star shine for millions of years. But at the same time, if there is a small deviation from the expected one, this star can turn into a black hole. And in his time, there was a popular physicist, Arthur Eddington. According to him, he completely rejected the idea of Subramaniam Chandrasekhar. He completely rejected it. Said, doesn't work. But when black holes were actually discovered, this man received Nobel Prize in physics. And he proved The pupil who thought that this man is giving a ridiculous idea. This idea is not going to work to decide the destiny of a star, whether it will live for millions of years onwards or it will turn into a black hole by a small perturbation. And for this, the man receives Nobel Prize. And the answer goes to the community that whatever the man was looking for, he has got it right. So this is how science works. This is how physics works. This is how we should move on in our lives so that we can make an impact. Even if you feel that you have not made any impact, maybe it will reflect at some point of time. But what is important here is your sincerity. With what sincerity you are working your problems. So this was it. Let's move on with our topic that we have been trying to understand. So what we have is we have this a n 1 of t equal to the integral of the matrix element containing the perturbation part in it. Right? Now, the first thing that we will discuss is if you have perturbation in constant time. So, we will be discussing constant perturbation. Constant perturbation. Now, when I say constant perturbation, this perturbation that you have introduced, it's constant in time, right? So if it is constant in time, you can get it out of the integral, right?
Yes, sir.
So what will be an 1 of t? This will be 1 by I h cross, and you will have a matrix M, H, P, N, and then you will be left with 0 to t e to the power of I omega m n t dash d t dash. Clear? Now what we have an exponential function inside the integral, and we have to integrate this, okay? So this part is out because this is constant. So from here we can move on. Okay? So I will have an 1 of t. This is going to be m h p n divided by I h cross. Now you integrate this. The integral of the exponential is an exponential, but you have to divide the internal derivative of the exponent. So for that, what you will get here, you will get e to the power of I omega m n t dash divided by I omega m n. So the limit will run from 0 to t. Clear? Right?
Yes, sir.
Yes, yes. Come on. Okay. So, what we can do here is, we would like to give the limits, and this iota will multiply this with this iota, it will give us iota square, that this will make our an 1 of t equal to minus m hp n divided by this h cross and omega n. Omega m n. Is this clear?
Yes, sir.
Fine. Okay. Now inside I would like to give the limits. So the first limit will be e to the power of I omega m n t minus e to the power of 0. Am I right? So this is your upper limit is t and the lower limit is 0. That should be the case. Now what we can do? Okay, we can use a limit, say e to the power of I theta minus 1. And if this theta tends to 0, this will give us 2i sine theta by 2. So I can use this formula in my equation, right? Yes. So because this is e to the power of 0, this is equal to 1. So for this, I'll be writing this. I can move on. So what you will have a1 of t is equal to minus the matrix m, h, p and n divided by h cross omega m n. Right? Then you will have in the brackets, you will have 2i sine square omega m n t by 2. Clear? Getting?
Yes.
Okay. So this is my amplitude. And you know, this amplitude, it's a complex thing, and we will always like to calculate the probability density. And probability density will be what? It will be more square of this a1 of t, right? So from here, I can calculate the probability density. Okay? So the probability density. Probability density. Come on. What will be that? That will be an1 of t whole square. Right? You will take the mod of square of this, and this will give us what? This will give us the probability density. So let's do that. So it will be the square of this, so this minus will go.
Yes.
Because you're taking the square of this. You will have the square of the matrix element. What will be that? That will be m, h, p, n divided by h cross square omega m n square. And this has its own square. Are you getting?
Yes, sir.
Then you have in the brackets 2. 2 will make it 4. I will write 4 outside. Okay?
Yes.
2 square. I have a square minus 1, but it's the mod of that. So that minus will also go. So what you'll be left with? You'll be left with sine square omega m n of t divided by 2. Okay? So this is your probability density. And if you will plot this probability of density, taking your y-axis, let me do it on the next page. Okay, this is clear up to this?
Yes.
Now, if we plot it, and on x-axis, we take omega mn. On the y-axis, we choose sine square omega mn t by 2. Now what you come up with? You come up with a pattern like this. The figure has not become that much beautiful, but you can understand it. Can you tell me what is this on your board? Have you seen this pattern before? What is it? Yes? Yeah, come on, what is it? It's the result of single slit diffraction. You remember that experiment?
Yes, sir.
If you have a light, you allow it pass through a single slit, then you have multiple interference things happening, and you have a central maxima, then you have a minima, maxima, minima, maxima. So you can see that you have your result is somehow looking like that of diffraction due to a single slit, and you can certainly correlate it. So this is our case when we assume that the time is constant. Okay? Now, so this is called constant time perturbation. This is constant time dependent perturbation. And now we would like to move on to harmonic perturbation. That means I will perturb my system with a harmonic function. Right? So the next thing that we'll be discussing is what? Harmonic perturbation. Okay. So what I have to discuss harmonic time dependent perturbation. Right?
Yes.
So in this case, what I will do, when my perturbation will become harmonic, I mean when I will perturb my system with a harmonic function. And let me choose that harmonic function as 2 sine omega t dash. Because when I am introducing a perturbation,
Yes.
it has to be harmonic. Okay? And why I choose 2? 2 gives me the mathematical simplicity. That's why I'm using 2 here. Different books will use different things. And you can have a problem based on the harmonic perturbation. This time I chose sine omega t. You can have a different harmonic perturbation that can be introduced in your system. But if we understand this, we can move on. We can move on to solve the problems based on harmonic time-dependent perturbation. Right? So, I have to start with my equation. So, what's going to happen? So, your perturbation is acting between 0 and t. There's no perturbation before 0. There's no perturbation after t. The perturbation is only acting for this span of time. Okay? So it's acting for 0 to t. So what will be my an1 of t? It will be 1 by I h cross. Then you have an integral 0 to t. Then you have the matrix element m, h, p, n. Then you have e to the power of I omega m n t dash, and you multiply it with by 2.
Yes.
And sine omega
T
dash. Now you see, the perturbation that I'm introducing in my system, I choose its angular frequency as omega, because its frequency will be different.
Yes.
Okay? And this is, the omega mn is the intrinsic angular frequency of your system. And omega is the frequency that you're introducing in your system.
Yes.
Is this clear to you?
Yes.
Now what I have to do, I have to solve this. And solving this will give me what? It will give me the amplitude, right? And then, once I get the amplitude, I will calculate the probability density. So, move on. So, what should I do now? I can rub this. Yeah.
It's a time
Now,
constant.
again, look at the things. The matrix element that we have here, we treat it as a constant. Because the perturbation that we have introduced in the system, we have given its value. It's 2 sine omega t dash. So what's going to happen? You will have a1 of t, then you will have 1 by I h cross out. The matrix element will be out. What you'll be left with? You'll be left with 0 to t. This 2 that you have here, okay, this 2 will come out. I will write it outside. Okay?
Yes.
And what will be left inside?
E of
Sine omega t dash e to the power of I omega m n t dash dt dash. Am I right? Getting?
Yes, sir.
Okay. Come on. Now I have sine theta. What is sine theta? E to the power of iota theta minus e to the power of minus iota theta divided by 2i.
Yes.
Right? So we have that formula. Sine theta can be written as e to the power of I theta minus e to the power of minus I theta divided by 2i. Clear?
Yes, sir.
Now I will use this formula in my integral. So what will I get? I will get a and 1 of t is 2 by I h cross. Then you have h m n. I will call it h m n. Okay. Then you will have integral 0 to t. Then you will have e to the power of I
Omega.
omega t minus e to the power of minus I omega t
Right.
divided by twice I, and then this will be multiplied by e to the power of I omega m n t dash dt dash.
इसमें t dash ऐड कर सकता है.
Yeah, here we have t dash. They're all dashes because I have to use the limit, right? So, what can happen now? You see this 2, we get rid of this 2 here. You got the rid? This iota square will make it minus. So a and 1 of t will be
Minus 1.
h m n. Do you get what h m n is? H m n is nothing but the matrix element. It is m
HPN.
h p and n. Right? So here you will have minus outside. That's it. Then you will have h cross. Clear? Now you can multiply these exponential functions, and what you will get out of that? You will multiply them. What you will get? You will get integral 0 to t. You will get e to the power of I omega mn plus omega times t dash, then minus e to the power of iota omega mn minus omega t dash. This should be the case, and you will multiply this by dt dash. Right?
Yes.
Getting? Come on. Okay. Now all I have to do is to integrate these exponential functions. Okay? So when you integrate these exponential functions, what you will get? Okay? Here I will get the rid of integration. I would like to get it off, and I will get the rid. The exponential will remain exponential, but it will be divided by the internal derivative.
Yes, sir.
That is iota omega mn plus omega. Is this correct?
Yes.
And here you will have iota omega mn minus omega. You see, come on, it has limits. The limits are running from 0 to t. Are you getting? Okay? So what will be the next step from here? Okay? You can see this iota. Okay, that's fine. Now you will give the limits. When you will give the limits, what you will get?
डैश नहीं है.
Yes?
dt डैश नहीं है.
Here is dt dash.
नहीं है. क्योंकि हमने तो
नहीं
इसमें
होगा.
Okay, sorry. Yeah, we have integrated it. Yes, you're right. There is no dt dash. There has not to be any dt dash because we have integrated it. Now we would like to give the limits, okay?
Yes, sir.
So when you give the limits, what you will get? You will get an1 of t is minus hmn by h cross, and here you will have a long thing, e to the power of I times omega mn plus omega times t. I'm giving the limits, okay? Divide by iota omega mn plus omega. But it will have minus e to the power of 0 term, right? And then you have minus e to the power of I omega mn minus omega times t divided by iota omega mn minus omega, and this will be minus e to the power of 0. Okay? I think I can leave it here now, because what you would like to do after this, you would like to calculate
plus e of 0.
here. No,
Minus होगा ना
no,
plus.
the minus is outside. I'm keeping it outside, okay? Then you can do it in the next step, okay? Then you can go on, and this will remain minus 1 and minus 1, and you can boil down this equation, right?
Yes.
And when you boil down this equation, then what you will calculate? You will calculate the probability density. What will be the probability density? That will be A1 of t. It's mod of scalar. Okay? Then this negative term will go out, and finally you will come up with an expression where you will use the limiting conditions. Okay? So the limiting conditions will give you the details about the result of this perturbation. I mean, if you directly resolve it, you will get a harmonic kind of nature of probability density. I think you can do it, you can proceed. Okay? So this was it. Anything else you want to tell me? Yes? So if I go back to the same thing, the same story about the candle, again I'm trying to tell you that it's your intuition, it's your interest, it's your focus that matters. Again, I would like to tell you that you can find infinite number of questions, and the example can be the same candle. The candle I started this lecture with, which I connected to the great Indian scientist, to the great scientist of this country, whom we call as Subramaniam Chandra Shekhar, who was given the Nobel Prize. Now look at this candle. If you have a candle in your dark room, what do you observe in the candle? The flame. But this flame it's upwards. The very first question that can arise in our mind is why this flame is upwards, why it's not in downward direction. Okay? And if there is a small whisper, there are changes in the flame. The flame that arises in your candle, if you are curious, you will certainly try to go back to your room. If you have some books, you will try to open the books. Maybe you will not get the answer, but if you raise the questions about the flame that's coming out of this candle, you will come up with infinite number of questions. And it is these questions that take you towards the table in your room where you have books. And you try to find the answers to those questions that arise in your mind. And this is how science progresses. And what I believe is that every society should be literate in science. If a society has a scientific mind, this society will certainly grow. It will cross the limits. Getting my point?
Yes.
Any queries?
Yes.
So with this, I would like to stop this discussion, and I hope you will proceed this lecture yourself, and you will try to solve some of the problems.